Okay, so last time we stopped somewhere here. So we are going to talk about protein synthesis, but we're going to discuss and think about these issues in the context of a cell. So this is a major difference between how we look at protein synthesis versus a biochemist look at the protein synthesis. They're only interested in enzymes, mechanisms. We're interested in the time and three-dimensional space. Okay, so when we look at the thing again, let's think about time and place, which is very important. So the amino acid, each amino acid has an N group, has a carboxyl. They're fairly stable. So if in order to stitch up two amino acids form a peptide bond, you have to overcome a high energy barrier. So one way to do that to use enzyme, right, to lower the activation energy cost. So in order to make tons of protein within minutes, you really need to have a very, very efficient way to do that. So therefore, inside the cell, you have a catalytic activity reside at the right time and right place to do things for making all proteins. So that's number one. And peptides are very diverse. That the diverseness is not because we have individual machines, each specialized for making a protein. We actually have only one machine. So the diversity lies in the details, how the machine operates. Machine gets instruction for making different proteins from where? From mRNA. mRNA got information from gene. And so that's messenger RNA. And then also need to interpret that instruction. So I have to translate that language, the mRNA language, into protein language. So there's a process of translation, how to extract the code, how to convert that code into actual action. What is actual action? To correctly polymerize one amino acid after another to make a protein. Okay? So that is, and also the chain, the polypeptide chain actually is elongated 1 unit at a time. You can't, for example, make two fragments and stitch them together. That's not how cells make proteins. You actually make it one at a time. Unidirectional. From which direction to which direction? N terminus, which corresponds to the 5' of mRNA, to the C terminus. So the last amino acid, the C terminus, carboxyl group terminal, is made last. Okay, and that corresponds to the 3' of the mRNA coding sequence. And error rate must be kept low. This is very, very important because you are making so many copies of proteins in a short time. Yeah, when we are in a hurry, we tend to mess up things. But cells cannot do that. The rate has to be kept low. So there are two ways to do that. One is you find a super quality control machine, just check everything at one step, make sure everything's perfect. Or you just have very redundant mechanisms. Each step will cut down the error rates. Okay? So you will see multiple steps where translation errors kept low. And also the production sites has to be suitable. I mentioned this, right? It's like you are making tons of stuff in one place, in one city. Then you create a logistic burden. You have to ship them all over the country to supply everybody. So if you do that, you have to have consequence. You have to meet the challenge, which is to ship them. But on the other hand, if you distribute your production in the proper place, then you reduce the burden of shipping, right? So there's an issue of where to produce them. So cells also have to face that issue. For example, the protein needs to be shipped to cell membrane to be secreted, translated at a different place, then those proteins need to go to the mitochondria. Okay. And then you have an issue of the efficiency and regulation. So that's very important to cell. Because if you're hungry, you don't want to waste your energy on protein that is luxurious. That's not essential. So you need to shut down those proteins. That's non-essential. And channel your energy to something that is essential to tide you over until the situation improves. And reverse is true. If you are well fed, you're well nourished, then you should take advantage of that to make all the protein to improve your fitness, right? So if you don't do that, you're wasting your good opportunity. Then the fitness of this species of this animal obviously is low. So there's a very, very tight regulation issue, and the regulation prefers to take place at certain steps, such as initiation. So we'll talk about how initiation of translation is regulated. Okay, all right. So now let's go through one at a time. So, machine for making all kinds of proteins. They are really, this machine is only slightly different between, let's say, human and bacteria. It's really is one of the remarkably conserved piece. Okay, so you have two subunits. The core contains this action site where mRNA, amino acids, tRNA all get together, interact with each other. The net result is making one protein after another. And you can see in this diagram which one is this one. Which one's better? About the same when you get the screen. So look at this one. This is actually a growing chain of polypeptide. It's coming out from this tunnel, little thing, and it gets pushed out. It gets longer and longer. And then you have tRNA positioned here, and then you have the mRNA. And this is the small subunit, the yellow one, and the large one is the big subunit. So kind of remember this overall thing that helps you to understand. Okay? So it's a very complex machine. And if you actually look at in vivo, you can't see that structure. You have to do structural biology to see. But under the EM, what you can see is little densely labeled particles. Those are ribosome RNA. And they're sitting along either on the surface of the membrane. Guess what membrane we are looking at? Some people may know. ER. These are ER membranes. So they are sitting on the surface of ER membrane. But some are floating around as a monomer or as a little short chain in the cytosol. So you have two populations. So for a particular ribosome, sometimes at a given moment of cell, a given moment of cell life, they might be attached to the membrane, and another time they may be floating. So for any given ribosomes, they can be either on the surface or in cytosol. But also at any given moment, you always see two populations of those ribosomes, because that's very important for the life of cell. Okay, so you have basically two kinds of production sites: cytosol or ER surface, ER membrane. And I think arrows point to those little ribosomes that sit on a single mRNA molecule. So you see actually a chain of little beads, string beads-like structure. All right, so this you know before. The two, if you purify ribosomal RNA and you do a fractionation, look at what components. You see two subunits, small and big, and small contains separate components, and large ones contain another subset of components. Depends whether they're from bacteria or from eukaryotes, the size are different, and the complexity is slightly different. You can take a look at that. Okay, so there are two kinds of macro components in the ribosomal machine. One is proteins, one is RNA. Now, if you look at this picture, since from the first lecture you're already well educated about the feature of proteins. Can you tell the golden color is protein or the silver gray color is protein? Can you tell just by looking at the protein structure? Which ones are proteins? The gold, the gold color? Okay, so those, if you believe those are proteins, they are on the surface. And the core, the gray-silver core, and you can tell these are kind of helical structure but disrupted a lot. What are they? What are those? Ribosomal RNA, right? Not messenger RNA. So ribosomal RNA. So ribosomal RNA contributes the bulk of the ribosomal machine. That's why it's called a ribo. And so these proteins on the surface, they generally plays a regulatory role. They're kind of modulate things. The core activity actually resides in the ribosome, including that catalytic activity that polymerize amino acids into protein. That activity actually is RNA based. It's not protein based. We'll come back to that issue later. Okay? All right. So that's how the machine look like. You have two subunits, large and small. And if you look at the nucleus, and you take a slice of the nucleus of a eukaryotic cell, and then you do an EM, if you're really lucky, you get a real nice picture. So that's one of them. This is sort of a picture we go onto the textbook cover. So what you see basically is this little particular region contains a fragment of chromosome that has some coding sequences for ribosomal RNA. So it turns out the ribosomal RNA coding sequences are clustered in a large intended section. So you have a huge cluster. So now imagine each gene is being transcribed and they are making ribosomal RNA. So you start to see like a brush kind of structure. So the longer ones, longer products, are the older transcripts, right? They're being transcribed longer. And then the short ones are the new. So you actually see so what you're here seeing is a simultaneous transcription of multiple genes that are in the cluster. And so each is making the ribosomal RNA transcripts. So the point is that the ribosomal DNA sequence is actively being transcribed. You need a huge supply of cells to make the ribosomes to supply for the translation machine. And this whole location is inside this little structure called the nucleolus, right? You heard that. Genetics talk about nucleolus. So what is a nucleolus? It's not an organelle. It's a specialized region inside a eukaryotic nuclei. And they basically contain lots of RNA and also proteins that go in. So I added several red arrows here. So this is the place where stuff goes in. Proteins involved in making this ribosome. So and then some RNA, and then most bulk RNA are transcribed in situ. So basically, this nucleolus then forms an assembly site to assemble large and small ribosomal subunits. And it takes a few components, which, for example, some proteins actually need to be translated or small RNA need to be imported from outside. And then after assembly, the final product of the small subunit and the large subunits, and they have to be exported outside to the cells, to the cytosol. Okay, so the nucleolus is the assembly site for making large and small liposomal subunits. And another level of regulation. So if you want to have protein made, you obviously need its mRNA. And that translation ultimately takes place in where? Inside the nucleus or outside? Outside. So then materials that initially made in the nucleus, that includes mRNA, messenger RNA, has to be exported. But we also know the initial transcription, gene expression, makes a product which is not mature RNA. They're precursors. So what's the difference between mRNA, which is mature form, messenger RNA, and the precursor RNA? What's the difference? Introns, I heard somebody say introns. So you have, they're not spliced, they're not processed. So there's a mechanism inside the nucleus that can recognize which ones are properly spliced and becomes mature messenger RNA, which are not. So the difference then is at the molecular level. The mature export-ready RNA have a bunch of protein that codes this ready form. And presumably, the unspliced form will have a different set of proteins that codes. So that provides a recognition mechanism for the gating, for the another gating mechanism to recognize who is mature. That makes sense, right? So the gating mechanism recognize mature messenger RNA which are ready to export based on the protein that codes them. So if they can get out, have a permission to get out, they can pass the requirement for gating by the gating method. Then they basically. So you can see this in this diagram. The mRNA that gets exported still contains some proteins. For example, the poly A, it contains the poly A binding proteins. It's not just making mRNA, actually mRNA for some proteins. And a portion of the protein actually get left over inside the nucleus and can be reused for exporting other mRNA. Okay, so there's a set of protein that directs export of messenger RNA. So there's an interesting, actually, phenomenon that initially puzzled the virologist. What happens is that, you know what is a retrovirus? What's the difference between retrovirus and DNA virus, for example? You know the difference? Is retrovirus contains RNA or DNA gene? Right. So that's part of the feature, defining feature. So retrovirus actually, if you purify the viral particles, it contains RNA gene. But then during their life cycle, they have a step which is mediated by DNA. So for example, HIV, right? When they infect the immune cell, initially it was the RNA gets injected into the cell. That's the RNA gene. And then this RNA will be reversely transcribed to DNA, and that DNA, the provirus, can be integrated safely into the immune cell. They can sit there for a long time. If you don't activate them, they can just replicate along with the host genome for a long time. And if the signal comes cause them to action, then this genome will make RNA. So it turns out they make two different kinds of RNA. One is a smaller piece called early gene transcript, and one is the gene, that's the packaging. So why do you need two pieces? The virologist wonder. It turns out the first piece helps the virus to get its genomic RNA out of the glucose. Remember, because the genome of the virus contains introns, contains the sequence that's don't look like mature. So they are stuck. They cannot migrate out. So they need a cheating mechanism to suppress the gating mechanism to get the gene out. So that's what the early gene. So what happens is that they make the early gene. The early gene RNA does not have introns. So it looks like a mature RNA. It gets out, and it gets translated, and it makes a protein called the RAD. And this protein is a nuclear localized protein. It gets sent back into the nucleus through a signal. And once in the nucleus, it can bind to a specific sequence of the viral gene. Remember, this is the RNA gene. And then serve as a passport. Okay, good. So that's so virus actually provides a very good alternative model to study cellular function. You can manipulate virus genome very easily. Actually, you can understand how a virus can bypass the cellular normal mechanism. And you understand how normal cellular mechanism works. So early days, we learned lots of molecular biology itself through using different versions of virus. Because each virus has its own issue. And when they're stuck, they have to find a way to solve the problem, just like us. Each person, you come to Athens, each will have a unique issue to solve, right? If you collect all the information, you understand Athens pretty well, okay? Good and bad. So that's the logic of using virus to understand cell biology. Anyway, so that's sort of a global kind of overview of the translation. Now let's look at the nitty-gritty. But that's biochemistry type of issues. So first issue is codon-anti-codon pairing. Because as I said, you have only one machine. And you have to make millions of different types of proteins. And that instruction is derived from the mRNA. So how do you actually execute that? So what happens is that you need readers that can read the codon existing in mRNA. So the actual molecule that execute that step is what? tRNA, right? You know that. The tRNA contains anticodons. So if you look at the three-dimensional structure of a tRNA, it's actually very technical. Because to tell you something, all the tRNA structures are very much look-alike in terms of global overview. Right? You have this inverted L shape. Remember that? Yeah? They all look very similar. And they folded very tightly. So this 3D structure, and you look from whichever dimension, actually looks very similar among all different tRNA, or between human tRNA and let's say fly tRNA. For good reason. Okay. And then also this tRNA structure is heavily chemically modified. It's not just regular nucleic. It gets modified. All kinds of modifications. So it makes this protein, the RNA structure, not only very stable, but also very unique on the surface. And that's very important. I'll show you why that's important. And then you have two important variable regions. One is the 3' end. So that sequence at the tip provides a unique information to tell an enzyme, I am the tRNA for arginine, or for lysine, or for methionine. So that is an important part of the variable region, okay? Because different tRNA is specialized for carrying different amino acids. And we have 20, right? So you need at least more than 20, actually different tRNAs in bacteria. And then also you have this anti-codon. So that's 3 base pair that have to match the codons. So these are very obviously variable regions. And so this is the table for your convenience. You already know that, right? Yeah, some amino acid contains more codons. So if you read the DNA sequence, sometimes you'll find different versions of serine, for example. You have 6 different versions. And others, they have only one, like the methionine and the tryptophan. So if you say UGG, that's for sure. That's for sure. Okay. And then you remember stop codons, right? UAG, etc. Okay. Now, in order for a stable pairing between codon and anticodon, we need a minimum number of hydrogen bonds. That minimum number is 6. So if you have more than 6, 7, okay. 8, fine, no problem. But minimum is 6. So if 6, so let's say you have this situation. You have, let's say this is A over U, okay? So there's 2 hydrogen bonds, right? Let's say this is G over C, so you got 3. And here, you just need extra 1. So if this is called a wobble. So that provides flexibility. So it doesn't have to be very strict. So that if you have some mismatch, it's still okay, as long as you contribute 1 more. So the third position is more flexible. The first and second has to be 100% match. Okay. So here are the possible mismatches that can be tolerated if it's at the position 3. And so these are the structures just for your convenience. AT, GC, and also I is for inosync. So that's the structure here. Okay. So these nucleotides can form obviously hydrogen bonds, right? In the formation of a ladder. So that's what the DNA ladder is. Base pairs are the ladders, and connected by these green bonds. Those are hydrogen bonds. Okay, all right. So that's codon formation. And then how do you charge the tRNA? Because I already told you the 3' end of tRNA is very important to carry the amino acids. So this takes place in the very important enzyme, which is highly conserved. This enzyme is called amino acid tRNA transferase. So what it does is basically transfer the correct amino acid to a correct carrier of tRNA. And it's highly specific, because if you mess up this, you mess up translation. Okay. So this step is a very important quality control step to keep the error low. And another thing is that if you notice interacting surface between tRNA, which is green, and the enzyme, which is blue, they're pretty extensive. Do you notice that? It's not just one small part of tRNA interacting with this molecule. It's pretty extensive. It's like use a hand to really feel a very large surface of chemical, which is a tRNA. That is the reason the tRNA structure has to be really, really stable and constant, because this enzyme recognizes that shape, 3D shape. And also the surface charge also provides information about which tRNA this thing is. Different enzymes will not interact with all tRNA. Okay, so again, it's like a protein-protein interaction determines the outcome. here the tRNA protein interaction with enzymes also determines who gets recognized and then amino acid to be delivered. Okay. This is a very important enzyme. And so this chemical reaction takes place because this enzyme can hydrolyze ATP and to charge a stable amino acid structure at the C terminus and make it generate a high energy bond. Because in order to stitch up two amino acids, you need to create a high energy bond at the C terminus one. So that's the first step. It costs energy, so energy is derived from hydrolyzed. So you store some high energy in this bond here. And then the next step is to basically transfer that destabilized amino acid, right? Because its C terminus now has this high energy bond, right? To the tRNA at the 3' position. So the net result is now this tRNA is charged at the 3' position. So that's what this is. So the enzyme does two things: create some energy to destabilize the then actually guide it to that position. So that's what the aminotransferase synthase is all about. So what if something messed up, like it put a wrong one? Because this happens, it's pretty easy to recognize different amino acids. They're hugely different, Some are really big, like glycines are really small, and glutamate is much smaller. They really don't make that kind of mistake. It's easy. What's difficult are those amino acids. They're almost identical and different slightly. Some have same molecular weight, it's just a little bit different isotope. So under that condition, you basically this kind of enzyme for that kind of amino acid creates another pocket for editing. So basically, you add this on. If it feels not quite fit, slightly too small, then that amino acid will be transferred to another pocket for editing. And indeed, if it's wrong, it will be removed and then send the thing back to the original synthesis site to add the correct one. Okay, so the editing mechanism guarantees even very, very similar but not identical amino acid will be recognized and removed. Okay, so this is a very important step, not only for making things, but also for quality. Once the tRNA is charged, now it's ready to participate in protein synthesis. And so you need now grow the peptide bond. Where is that located? Ribosomes. Right? So this last step needs to take place in the ribosome. So the reaction is really pretty straightforward. Basically, let's say you already have an existing growing chain of peptides. You have 1, 2, 3 amino acids already existing. Let's say this tRNA is still hanging there. So now the next step is basically get rid of this tRNA and then condense this amino group of the new amino acid to the C terminus of the growing chain. So pretty straightforward reaction. It's a condensation, very much. So, but it costs energy. In order to do this efficiently, you need an enzyme. So this is how it works. And then, okay, this is the second part. Then you want to get rid of the RNA, as I said, and it forms the new chain. So that's pretty straightforward. This is a reaction, okay? But The problem is you need to do it really fast, and massive. That's the issue. So you do this through an enzyme activity. What's unique about this enzyme activity is it's not protein-based, it's RNA-based. Because I already showed you the ribosome structure, right? The core are all the RNA. And that catalytic site resides on that core. So it's RNA, it's a ribozyme. And so this is how it works. So basically, ribozyme contributes a adenine group. And it forms a hydrogen bond between this tRNA, and then which is the donor is coming in, and also the nitrogen atom in the atom. So this loosens up and causes this amino and the nitrogen atom to attack the base carbon, the carbon atom here, to destabilize the double strand bond. So you create this transient structure. And this transient structure is not stable, so it gets stabilized by have this protons attack this oxygen atom in the old tRNA, then that one that needs to be get rid of. So the final result is you have a new amino acids added and old tRNA removed. Okay, so that's what the ribozyme is doing. That sits in the machine. So basically now you can envision a situation like a movie. So you have a machine, large subunit, two small subunit. mRNA is somewhere in the middle, sandwiched in between, right? And then you constantly have things in and out. What's in are the tRNA carries the amino acid. What's out is the old tRNA that finished the job, gets dumped off. And so in this catalytic site, that remains relatively, you can think of it as a fixed spot, right? And so you have things coming in and leave, and so what's really busy are this catalytic site. So you have a traffic in and out. So that's how it works. So the machine just wait there for things to come in, for the tRNA to get rid of tRNA. And then polypeptide chain goes longer and longer and it gets pushed out. So that's what it is. Yeah, it's like a workshop. You have in and out things. All right. And then so here's a diagram showing that. So if you look at the structure of a ribosome, maximally you can fit in 3 tRNA. So these are the 3 sites from the top view. But at any given time, you only see 2 sites occupied. One of them is just for transition. Okay? So that makes sense. One tRNA is the one that needs to be removed. Another tRNA is the one that come in and you need to replace the old one. So at any given time, you have 2. Okay? And then every time you get rid of one old tRNA, you add a new one. Then the machine slide along the mRNA and move on to a new codon. Or mRNA gets pushed the other way. It's a relative motion, whichever way you look at it. Either the machine moves along the mRNA towards the 3' end, or you can say the mRNA gets pushed. So that's the diagram showing that, the action. So you can take a look at it yourself. Okay? So at the end, you basically, by sliding the ribosome subunits, big and small, you create a new empty site for a new RNA to come in. Okay, so yes. Oh. This one?
Yeah, just those 3.
That's. So basically, okay. So this is a transient structure. It's not very stable. Okay? It's an intermediate structure. It stays alive for a very, very short time. And the enzyme contributes to this adenine group to create this transient structure. The reason is you can have a formation of the hydrogen bond with the oxygen atom in the structure. Okay? So that will cause the break of this bond. So the old tRNA that used to be linked to the peptide chain removed. So that's what it is. Okay? So it's like any catalytic reaction. Go back to your biochemistry book. Okay? Look at these reactions. So what happens is that the electrons get moved around. Right? The electron is evenly distributed. Yeah. So what the adenine does is shift the electron from a stable position to an unbalanced situation. If you really want to know this, go back to your any chemistry book to read about how covalent bond can be broken. Okay, so it's very simple. Okay, just I don't have time for that. That's why we require prerequisite includes biochemistry. Okay, so now continue with biology. So what we're interested in now is to understand the quality control and the regulation of synthesis. So in order to understand that, first we have to understand how translation is initiated. So basically, at the very beginning, you need to form a complex that contains initiation tRNA or initiator tRNA, right? Remember that? Okay. And then small ribosomal subgroup, and then some protein factors called initiation factors. You have different names. And also has a GTP. So you have multiple components together form a complex. That complex is absolutely important to initiate translation. It's necessary, not sufficient. Okay. So once you have a complex form, and then this thing will bind to mRNA, and in the following way. So basically, this mRNA first also needs to be properly form a structure. So the diagram here shows a loop. So what does it mean? It means the end of this mRNA and so the head and the tail of this mRNA actually are kind of interacting with each other. So that's how they form a loop. So that mRNA is competent for translation. If it's not like that, it's no good. It will not be translated. Now think about what is the advantage to have that kind of structure. Why do you want to have mRNA with head and tail interacting together? Yeah. Okay, that's a good guess. Any other reasons? Why do you selectively translate these looped RNA, which has a head and a tail interacting? Foreign RNA, is that what you? That's a reasonable guess, I would say. Any other reasons? Yes. You're almost there. So basically, it prevents from translating broken, fragmented, therefore non-functional mRNA. You don't want to translate broken mRNA. That's a waste of time, right? And actually worse than a waste of time, it creates garbage. It's very expensive to clean up garbage in the cell. So actually you absolutely don't want to do it. So this is a clever way to guarantee the mRNA to be translated is intact, because it has a head and a tail. Now obviously, you say FR mutagenesis, that doesn't matter. The cell can't tell. Okay? So this is the reason. Now, the first step, obviously, now gets interesting, right? So you have a ready-to-go small subunit carrying these factors, and then you have a ready-to-go mRNA, and then it gets interaction takes place. And another important thing is the 5' cap. So the 5' cap defines the beginning of the transcription machinery where it sits. So it defines the cap. So now you've got this structure here. The head, tail, the cap. But sometimes AUG, the initiation codon, can be really close to the cap, but sometimes can be far away. Okay, over long distance. So this distance is kind of flexible. As long as you have a cap, the machine can start to glide along the mRNA and eventually decide this is the AUG I want. Now, what if you have a multiple AUG in tandem? So somehow the sequence is evolved in such a way, you always find a predominantly translated AUG. So sometimes you may see minor translation products that start from a different AUG. Not necessarily the first one is the best because of surrounding sequence, but they always evolve to have a dominant AUG. Okay, so they find AUG, and this is the time when the large subunits is coming in. Okay. So somehow finding the AUG recruits the large subunit. Now the machine is fully functional, ready to go, and do the translation. Now remember, the first AUG, the initiator mRNA, is always creates this this first initiator mRNA, and they do not. Okay, let me put it this way. If you look at all the amino acid proteins, the first amino acid is not methionine, because that initiator does not provide the methionine. So either the methionine is transient there, gets removed, or it's just an initiator. It doesn't provide methionine. That's why not all proteins have a methionine as a starting amino acid. So anyway, so now the translation starts after they find initiation codons. And the next, okay, so before I go on to elongation, let me say something about the bacteria. So bacteria does not have a 5' cap. So it uses a different way to find AUG. So this is the way that bacteria is done. It actually has internal ribosomal binding sites. In other words, the ribosome machine recognizes the sequence on the bacterial mRNA. So if the bacterial RNA has multiple ribosomal binding sites indicated by red, and have multiple initiation codon and stop codon, you can create a situation that one mRNA can encode multiple different proteins. So that kind of a thing is called a polycistronic. So polycistronic means a mRNA can have multiple coding sequences, each encoding a different protein. So this is because the initiation mechanism in bacteria is very different from eukaryotes. Okay, elongation. So after initiation, the elongation is relatively straightforward. So you just need energy, and you need a factor to push the translation forward by gliding through the codon one at a time. But there's some quality control steps. So the elongation factor also actually provides at least two known ways to improve quality control. So if the amino acid, the tRNA pairing codon and anticodon are not quite right, and it will slow down things that triggers hydrolysis and dissociation. So the elongation factor will start again. And also the energy they're required to make protein is not ATP. What is it? It's on the picture here. It's a GTP. Okay. And so the ribosome also contributes to the correctness of the codon-anticodon pair because they simultaneously interact with both. So if the pairing is perfect, that interaction, that triangle is perfect. So then it's good. If it's slightly unfit, then it slows down things and it stops. We can restart again. Okay, so the bottom line, elongation also provides a layer of quality control on top of other steps we have described before. Now, at the end, the protein translation has to find a way to stop, right? Otherwise, you're making really, really, really long ones. So that comes to termination. Now, I have a picture here showing two molecules. I'm asking you to look again. Which one is a protein? Which one is a non-protein, such as RNA? Which one is protein? The one on the left is a protein. I think that's a protein. Yeah. So this is a protein in the shape of a tRNA. That protein is termination factor. So at the end, when the ribosome glides and encounters the last codon, that stop codon, instead of a tRNA going in, you have this termination factor that inserts in that position. So that's depicted here. So that factor, which is red, binds to that anticodon sequence position. And as soon as that binds, everything falls apart. So now the small subunit, large subunit dissociate, everything falls apart. The mRNA is ready for another round of translation, which actually already taking place. We'll have that picture in a bit. So what happens to those large and small subunits of ribosomes? It gets recycled, reused to make other proteins, along with other factors. Okay. So that's how translation process goes. So we're more interested in quality controls and its regulation. Okay. So this diagram actually shows for each mRNA, because they're fairly long, they can accommodate lots of ribosomes. So you don't have to wait until one round is finished to start a new one. What happens actually, you have lots of ribosomes and simultaneously translating this same mRNA. So obviously the product length is different, right? If it's a mature, you get a full length protein, and otherwise you get a little bit. So it's a gradient, basically. So this kind of polysome actually can be useful to study gene expression as a tool. So let's say if you can isolate these things, polysomes, you actually can say these are the mRNA that we activate, right? So if you have two population cells, you say who is making more certain type of mRNA, you can actually just try to isolate polysomes from both populations and do a comparison to see which pool has more of this particular gene. And then you can argue, say, this population cell has more active expression of this particular gene, or a population of gene. So polysomes actually are very good, useful reagents to study gene expression. So this slide shows one example how a cell can regulate its protein synthesis through its initiation step. So let's look at the top panel. What does it say? So this is an inactive factor. It binds to GDP. So the binding is very tight. If it binds to a GDP, this protein is inactive. It's silent. So now, in order to activate this protein, this is an initiation factor, which is essential, remember, for the first step. So if you don't have that factor, it's all inactive, then there's no translation. And so in order to activate this thing, you need to recruit something else. This is another initiation factor, 2B. The 2B is basically can bind to this factor and help to dissociate GDP from EIF2. So binding and dissociation, that's all it is. And once this happens, and this protein now can bind to GTP, and GTP binding leads to the active form of EIF2. So this convoluted way is really just to make one simple thing, to replace GDP with GTP. But why do you need this whole set? Because the binding is very tight. So in order to get rid of the GDP, it actually costs energy using another to do this. So this kind of GTP, GDP on and off switch takes place all over signaling pathways. Have you encountered an example before with Dr. Schultz? Okay. So you will see many, many, many examples. Okay. So in order to get, so this is this factor is called the GAP. So this is the guanidine exchange factor. So it's called a GAP. Okay, lots of gaps. And then there's also another one that does the opposite thing. So next time when I have an example, I'll show you. Okay, so the 2B is a gap. It helps to remove GDP, and then the GTP will bind and activate. Now, let me ask you a question. Why you remove GDP, you somehow guarantee GTP will bind. Why cannot be another GDP? Yes. They're pretty high for both. So guess another reason. Yeah. So the ratio between GTP and GDP is at least 1,000-fold in the cell. So as soon as you lost GDP, it's always over. You have a more than 99.9% chance of GTP. So that's why. Okay. Now, what if you have a different situation? Here, for example, you have this inactivated form, and it gets phosphorylated. So the bad news about phosphorylation of this protein is that it prevents 2B from doing, 2B can still bind, but from doing activation. So now you basically sequester 2B. If you phosphorylate, the initiation factor 2, right? So if you have that kind of situation, what happens is you'll deplete GAP, that 2B, because everything will bind to a dead protein and it will stuck in power. So that will basically downregulate translation. Or if it's essential and you deplete 100%, you basically kill the cell. So usually you do the downregulation. So this is actually a way of downregulation until a phosphatase come along, can remove that phosphate. Then it can rescue the situation. So the kinase, along with GAP, forms a mechanism to switch on and off translation. So that's just one small example. There are gazillion ways that they can regulate the translation initiation. Okay, So I think that this is one of the last slides. So I just want to mention this uncle gene called the TOR. So this uncle gene is upstream from multiple subpathways. Each regulates initiation and translation. So it's a master regulator. As you can imagine, if this gene function is essential for so many of these pathways to leads to translation, and if you block it, it's obviously bad. It's really bad for translation. It cuts down the translation level very, very hard. But on the other hand, if you overly produce this mTOR, then you get translation going gangbusters. Right? So this is what you need. What the cancer cell? Because the cancer cell will need to grow very fast. They replicate very, very fast. So they need tons of proteins to support that lifestyle. So that's oncogene. So if you have a mutation that causes mTOR to be very, very active at a very high level, that's cancer cell. So, but that also is an opportunity to kill a cancer cell. So if you find a drug, like the rapamycin and other chemicals that can inhibit, bind to mTOR and downregulate function, then you can kill cancer growth. Okay, so this is one example of how translation can be misregulated by a cancer cell, and how that can be a drug target. And finally, come back to virus again. So the virus has this trick. So this virus can abuse the system by recruiting the machine to work for the virus itself, but slow down the host translation. So how does that work? So it works by cutting this another initiation factor, this type 4 gene, into a smaller fragment. So this protein then, once it gets cut, it can still bind to the viral RNA structure, but it cannot bind to the poly-A tail because this protein has more than one domain. When one domain cuts off, another domain is still functioning. So it can bind to the viral genome and cannot bind to the poly-A tail. So what happens if you cannot bind to poly-A tail? No translation, we just talked about, right? Because the initiation requires head and tail interacting together. So the host translation gets shut down to a large extent. But the viral genome now gets translated because this thing can bind to the ribosomal entry site in the viral gene. So it turns the host machine into a viral machine to translate viral protein. Okay, this is the last slide. That's it. I don't think it's lost.